The last reaction that we'll look at, or the last type, as we classify them by the process of change, not just reactants or products, is oxidation reduction. And as we said, 4 of the 5 types, if we were just looking at reactants into products, or the cheat sheet that we used in first year chemistry, would be considered oxidation reduction. Because really, gaining and losing electrons is a lot of chemistry and a lot of the process of bonding. And it's when we're breaking and making bonds that we are doing a chemical change. So oxidation reduction has to occur together. And the reason they occur together, much like Bronsted-Lowry acids and bases, is that they involve the transfer of something. Oxidation is defined as the loss of electrons, and reduction is the gain of electrons. It's called oxidation because it was initially associated with when metals oxidized or reacted with oxygen, maybe rusted. And when they do that, they are losing their electrons, oxygen's gaining them, and then they're forming that oxide. But really anything, oxygen included or excluded, could be an oxidation. It gives its electrons to the thing being reduced, and the reduction gets its electron from the oxidized species. It's not a step-by-step process. We treat it as if it's occurring totally simultaneously. So the way that the mnemonic device that I like for this, and there are several, is that Leo the lion says grr. Losing electrons is oxidizing. Gaining electrons is reducing. So Leo, lose electrons, oxidize. Grr, gain electrons is reduction. But if we look at a lot of reactions, and we can skim back and find some good ones right here, it's not obvious what's gaining or what's losing electrons, maybe in this example right here. Nothing has an obvious positive or negative charge as we look at the overall reaction. The same is true on all of these reactions, even though out of these 4 reactions on the screen right now, 3 of them are oxidation reduction reactions, or sometimes we would call those redox reactions. So the trick that we use to help know whether something's oxidized or reduced, meaning gaining or losing, is kind of looking at its charge. So we've done this a lot using the periodic table. The alkali metals tend to form +1s, the halogens tend to form -1s, and they do that because they're likely to exchange electrons to fill their outermost energy levels and be like a noble gas. All of that's still true. In ionic compounds, that tells us what the charge is. Our charges are really equal to the charge of the cation and anion. That's the oxidation number. The trouble, quote unquote, comes in with covalent compounds. Something like water, or maybe even more confusingly, something like nitrogen dioxide. We don't know, is oxygen or nitrogen gaining or losing the electrons, because we don't define it that way. We say that they're sharing the electrons. So this set of rules here that we'll practice and apply allows us, whether it's ionic, covalent, an individual element by itself, or looking at the reaction as a whole, to know what's gaining and losing. So first and foremost, when an atom or an element is by itself, it has no charge. So if it just says Na, it's not bonded to anything and it doesn't have any superscript, even though that's in column 1, that atom of Na is neutral with a charge of 0. If it says O2, because we've got diatomics, so the oxygen that we're breathing in and out, the nitrogen that we're breathing out, even though they can form ions, the gas itself, even as a diatomic, is neutral with a 0. If we have a reaction that shows the charge on the ion, and we showed a couple of those previously, maybe it would be a net ionic equation, maybe a precipitation reaction, any of those, the charge on an ion that's just floating around by itself is exactly what it says. Down here is what we start to get into for compounds. There's kind of a hierarchy of what's likely to happen. In compounds, no matter how it bonds, ionically or covalently, fluorine, as the king of attraction for electrons, is always a -1. The other halogens are almost always -1, but there are cases where they are not, sometimes even when they're bonded to fluorine itself. Oxygen's almost always -2. One exception would be if it was with fluorine in a way where that doesn't work out. Another would be a peroxide. We'll deal with hydrogen peroxide, one that you've heard of, and there's a few others, but every now and then oxygen can form a -1. So we have to look out for peroxides, but the general rule and what we'll go forward with in 95% of compounds, maybe even 99, is that oxygen is -2. Hydrogen's almost always +1. If it is with a metal, if it's in a special compound called a hydride, it could be a -1, but that's rare. So once again, 99% of the time, these elements, fluorine, oxygen, hydrogen, we're giving them the charge that they want. The other thing here is that when we have a compound, if that compound is neutral, all the charges, all the oxidation numbers have to add up to cancel each other out. We know that. That's how we write the formulas for ionic compounds, but that's even true in covalent as we look at oxidation numbers. If we have a polyatomic ion, either by itself, floating around, maybe in a complete ionic equation, or as a part of a compound, the sum of the oxidation numbers, sometimes called oxidation states, add up to the charge of that ion. Nitrate, NO3 -1. The one nitrogen and 3 oxygens together, when we add up all of those oxidation states, they have to add up to -1. And we'll practice and see how that happens. But some general tips. These are kind of our hard and fast rules. Metals are almost always based upon their charge. There is so few exceptions, we will treat it for our purposes as if there's none. Non-metals, here it says in binary ionic compounds. That means if it's bonded to just one metal, so I've got a metal and a non-metal, then we use our ionic rules. It's a piece of cake. They're ionic charges. It's once we start to get polyatomic ions, transition metals, and covalent compounds that oxidation numbers are a little bit harder to know. And that's where we start to look at these rules up here and work by process of elimination. For example, in nitrate, if we had 3 oxygens, each of which was -2, but then we also thought of nitrogen, which is in column 15 as a -3, -3, -2, -2, -2 doesn't add up to -1. It adds up to -9. That's how we can know that in that instance, nitrogen has a different oxidation number. So what we're doing right here is those polyatomic ions and covalent compounds, especially those nonmetals, kind of in the middle of the nonmetal section, carbon, nitrogen, phosphorus, sulfur, selenium, sometimes even chlorine or bromine, they might have a different oxidation number than the ionic charge we're used to. And by following these rules, we can figure out what it is by knowing what is gained and lost. One thing that we don't have here that is important to talk about, running out of space there, is that the reason we use these numbers and call it oxidation, and we'll see this as we apply it, is that when the oxidation number goes up, it happens because it is higher in charge. It has increased in charge, or we'll put an up arrow oxidation number. So I am going to add that in. That will be there for you. And then this one will be down arrow oxidation number. So oxidation number is kind of our cheat here, where we don't necessarily have to look at the gain or lost. If it went down, it was reduced. So that's a way that we can shortcut here, but also know what's happening to our electrons. So in the next one, we'll apply this even further, but really when we can jump in and practice this is when this makes the most sense.